For 4 years, the historic planet-hunting mission Kepler stared at a group of 150,000 stars located in a region extending 3,000 light-years away from Earth. The data collected by this spacecraft has brought a turning point to the long search for other planets like Earth. Is ours one of countless life-bearing worlds strewn about the galaxy? Or is it a rare Garden of Eden in a barren universe? What are we learning about our place in the cosmos? From the search for Earth-like planets. Tens of thousands of years ago, humans began to fan out across the planet, following unknown pathways, crossing unmeasured distances. We traced coastlines and sailed uncertain seas. We crossed ocean straits drained by an ice age. Into every corner of Earth we ventured, looking for places to put down our roots, to raise our families, or just to see what was there. Today, it's the final frontier that fires our imaginations. With so many stars in our galaxy, we make a simple extrapolation that the cosmos must be filled with worlds like ours, with life, even intelligent life. This so-called many worlds view goes back to ancient times, to China, India, Greece, and Egypt. The Quran, the Talmud, and many Hindu texts all imagined a universe full of living beings. It wasn't until the 16th century that the idea became grounded in concrete notions of the physical universe. Astronomer and mathematician Nicholas Copernicus declared that Earth revolves around the Sun. That opened the way for the Italian friar Giordano Bruno, a natural philosopher who believed that the universe is eternal and without end. He held that there is a multitude of worlds with diverse life forms, including intelligent beings. Bruno's outspoken challenges to church doctrine got him executed in the year 1600. His ideas gained support when Galileo Galilei used his telescope to show that our sun is just one among countless other stars. By the modern era, the many worlds view held sway in scientific circles. New telescope technologies gave us a view of vast star populations within our galaxy. As the astronomer and author Carl Sagan noted, given the sheer number and diversity of stars in our galaxy, it's far more likely that the universe is brimming over with life. In 1961, the astronomer Frank Drake sought to lay out the odds of finding advanced alien civilizations. The Drake equation took into account the rate of star formation in our galaxy, the fraction of stars with planets, of planets that might support life, that might develop intelligent life, or radio communications, which we could perhaps detect. Even as astronomers began to scour the heavens for alien signals, another view of the galaxy gained momentum. It started with the philosophers Aristotle and Ptolemy. They believed that humanity and Earth are unique. With the spread of Christianity, this Ptolemaic system became embodied in the rare Earth hypothesis. In religious doctrine, it was taken to mean that mankind and Earth were specially created by God in His image. In science, it implied that the circumstances that allowed life to unfold on Earth are so particular and fortuitous that the odds are slim we'll find another place like it. Where does the debate stand today, with information about Earth and the cosmos pouring in from ever more advanced technologies? On the many-world side, modern theories hold that planet formation is a common byproduct of star formation. And as we've seen on this planet, life is persistent, adaptable, relentless. Millions of species grace the landscapes and oceans of our planet. From simple one-celled plants to complex megafauna. In terms of mass and sheer numbers, none of it holds a candle to a simple hardy form. Bacteria have been documented in fossils dating back some 3.5 billion years. Bacteria are found in habitats ranging from hot springs and volcanoes, the digestive systems of animals, the soil, or the sulfurous environments of deep-sea hydrothermal vents. They are part of a much larger global ecosystem that suffuses the Earth's crust. Down where heat and chemicals from Earth's interior fuel their growth. Not even the worst climate catastrophes of the past could dislodge this biological storehouse. From widespread volcanic eruptions to episodes of global glaciation. It's easy to imagine life gaining a foothold on a wide variety of worlds. Comets and asteroids, for example, have been found to deliver a steady rain of interplanetary dust to Earth, including organic compounds and water that could have supplied the building blocks of life. Analyzing a type of carbon-rich meteorite, researchers have found amino acids, molecules used to make proteins. They also found components used to make DNA, along with sugar-related organic compounds that are a basic part of living cells. But primitive life forms don't necessarily evolve to more advanced forms. The rare Earth view points to a complex and fortuitous chain of circumstances on this planet. It began when simple bacteria gave rise to one-celled organisms called eukaryotes. They evolved specialized internal organs to regulate processes such as photosynthesis. These organisms began to regulate surface temperatures by taking in carbon dioxide, a greenhouse gas, while releasing oxygen. Volcanism and other geological processes released more CO2 in the air. Ocean and land plants, along with chemical reactions in rocks called weathering, pulled CO2 back out of the air. A global carbon cycle developed that kept surface temperatures within a relatively narrow range. A stable climate allowed the planet to retain its stores of water. Water, in turn, has helped drive the movement of Earth's crustal plates, a process that releases and buries CO2. There were other factors as well. A nearly circular orbit has helped keep seasonal extremes in check. The Moon stabilized the day-night cycle. Earth is also at a distance from the Sun that allows surface temperatures to hover between the freezing and boiling points of water, the so-called habitable zone. Some scientists also believe we live in a galactic habitable zone. We are close enough to the galactic center to be infused with heavy elements generated by countless stellar explosions over the eons, but far enough away from deadly gamma radiation that can roar out of the center. At the same time, Earth has been able to survive a range of other natural hazards. Some researchers, for example, have linked mass extinctions in the past to the Sun's passage through one of the spiral arms, where gamma radiation sources lie in wait. So too, we've made it through asteroid impacts, climate changes, and solar eruptions. Now we wonder, are there kindred spirits somewhere out there to share our survival stories with? Or is Earth alone amid the wastelands of a barren galaxy? This image shows, in stark relief, the biggest obstacle faced by planet hunters. We're looking at Earth, as photographed by the Voyager spacecraft from a distance of 3.7 billion miles. Our mighty world occupies only about 1/10 of 1 pixel. Try seeing something this small at hundreds of thousands of times that distance. And try seeing it through the bright glare of a star. Still, astronomers have made extraordinary progress. In 1995, Swiss astronomers announced the discovery of a planet orbiting the star 51 Pegasi. They found it by carefully charting the star's wobble caused by the gravitational tug of an orbiting planet. What they found is no Earth. It has about half the mass of Jupiter, but orbits at a distance closer than our own Mercury is to the Sun. Most of the planets discovered with this method are gas giants, so-called hot Jupiters that swing in close to their host star. "51 Peg is a G-type dwarf star, like our Sun. It is brighter and more massive than 85% of all other stars in the galaxy. But there are only about 500 others like it within 100 light years of Earth. Scientists have turned their wobble method on a more plentiful breed called M-stars. One of them, 20 light years from Earth, is too dim to see with your naked eye. Gliese 581 in the southern constellation Libra is a red dwarf with 31% of the Sun's mass, but only 1.3% of its luminosity. Using the wobble method, the Swiss team detected an entire solar system with up to 6 rocky planets, ranging from 2 to 18 times the mass of Earth. The most enticing is Planet G, whose presence is still unconfirmed. It's within the life zone. But a star like this gives off so little energy that a planet would have to orbit close just to get enough heat to power its climate. That subjects it to solar flares, common in small stars. So too, a close orbit increases the tendency of the star's gravity to halt any spinning motion. That makes it more difficult for heat and moisture to circulate, and a habitable climate to form. If planet hunters operating on ground-based observatories have told us anything, it's that planets and solar systems are highly diverse. The search for Earth-like planets requires a larger sample. Enter the Kepler Space Telescope, launched in the year 2009. For nearly 4 years, astronomers aimed its precision instruments at a tiny patch of sky with 150,000 stars at a distance of up to 3,000 light years away from Earth. Kepler used what's called the transit method to record subtle dips in the star's light caused by a planet passing in front of it. By analyzing the light as it dipped, scientists are able to estimate the planet's mass, radius, and the distance from its parent star. Combining Kepler and ground-based observations, there are now 3,841 planetary candidates. 1,075 have been confirmed by further telescope or computer analysis. The vast majority of candidates orbit in the hot zone of their parent star, and most have a mass equivalent to Neptune or Jupiter. There is a smaller cadre of planets out in the warm or habitable zone. These two are mostly large gas planets. About a dozen, though, have masses that are smaller than Neptune, but larger than Earth. At the higher end of this range, they are known as mini-Neptunes, or gas dwarfs. At the lower end are rocky worlds called super-Earths. How Earth-like are they? Most super-Earths are thought to have dense, inhospitable atmospheres. That's because their intense gravity is able to hold on to stores of gas drawn to it in the early days of solar system formation. If a slightly smaller planet can avoid this fate, it may succumb to another. Consider the star Kepler 62, a relatively Sun-like star with 69% the mass of our Sun. 2 of its 5 known planets are most likely solid like Earth, but with large amounts of surface water. 62F on the outer rim of the habitable zone could well be frozen over. 62E, farther in, is likely inundated. The thinking is that the density and internal heat of a planet this size prevents surface water from migrating down into the mantle. With land areas kept to a minimum, a super-Earth would not develop the carbon cycle necessary for regulating a climate. It may be too early to write these worlds off. A recent study showed that the weight of their oceans may be enough to push large amounts of water down into the mantle, where it could help fuel volcanism and plate tectonics. These geological processes would create land masses, allowing a carbon cycle and a climate to take hold. So far, we have not seen what we're looking for: Earth 2.0. A malfunctioning gyroscope on the Kepler satellite ended its observations after 4 productive years in space. The data it captured remains a mother lode that scientists continue to mine. Based on a statistical analysis of all the Kepler observations, a new study says 1 in 5 Sun-like stars do have planets about the size of Earth, with surface temperatures conducive to life. Given that about 20% of stars in the galaxy are Sun-like, that would amount to several tens of billions of potentially habitable Earth-sized planets. And there may well be a whole other population of habitable worlds we haven't considered. 620 light-years away, in the constellation of Cygnus the Swan, is a star that's slightly cooler and smaller than our Sun. Kepler 22 has a planet squarely in the habitable zone, but at around 6 times the mass of Earth, it's probably enshrouded by a dense atmosphere. It's large enough that it could have pulled another planet into orbit, one that's large enough to maintain an atmosphere and liquid water on its surface. If any of the confirmed exoplanets do have a moon, it would leave a subtle but distinct imprint on the star's light. Kepler came online in a new age of massive data gathering and supercomputer analysis. That will define future planet-finding missions as well. The Transiting Exoplanet Survey Satellite, TESS, for example, is scheduled for launch in 2017. It will focus on about 500,000 bright sun-like G and K stars, looking for telltale dips in their light as orbiting planets pass. The James Webb Space Telescope, in active development since 1996, is currently slated for launch in 2018. Astronomers hope to use it to peer into planetary atmospheres, to detect carbon dioxide, oxygen, methane, and other indicators of climates or even life. Optimism that we'll find other worlds like ours is driving these increasingly sophisticated efforts. It's tempered by what we've learned of our own world and solar system, that there are so many factors that can derail a planet's evolution. In the future, if our itch to explore becomes unbearable, or if somehow things don't work out on this planet, there is bound to be some available galactic real estate out there. We'll have to develop advanced transport to get there, 20, 100, 1,000 light years away. We may find that we are not exactly adapted to its gravity. Its mix of land and water, its atmosphere. We may not prefer its climate. The question is, will it be worth the trip? We crossed ocean straits drained by an ice age. Into every corner of Earth we ventured, looking for places to put down our roots, to raise our families, or just to see what was there. Today, it's the final frontier that fires our imaginations. With so many stars in our galaxy, we make a simple extrapolation. Tens of thousands of years ago, humans began to fan out across the planet, following unknown pathways, crossing unmeasured distances. We traced coastlines and sailed uncertain seas. That the cosmos must be filled with worlds like ours, with life, even intelligent life. This so-called many worlds view goes back to ancient times, to China, India, Greece, and Egypt. The Quran, the Talmud, and many Hindu texts all imagined a universe full of living beings. For 4 years, the historic planet-hunting mission Kepler stared at a group of 150,000 stars located in a region extending 3,000 light-years away from Earth. The data collected by this spacecraft has brought a turning point to the long search for other planets like Earth. Is ours one of countless life-bearing worlds strewn about the galaxy? Or is it a rare Garden of Eden in a barren universe? What are we learning about our place in the cosmos? From the search for Earth-like planets,